Thanks for the nice introduction. So my talk today is about the design and characterization of a new absolute diffuse reflectance reference instrument that we're working on. I should say that this is very much an ongoing project, so if anyone has any bright ideas or dire warnings, I'd love to hear them. The outline is as shown. I'll start by telling you a bit about the why and the how about realizing a diffuse reflectance scale, why this is something that we're interested in. I'll tell you about the modified sharp-little method, which is an integrating sphere-based technique that we use to do this. I'll describe in some detail our new instrument, and then show you some preliminary performance data addressing these common sources of uncertainty: wavelength scale, spectral bandpass, and nonlinearity. So probably this is overkill for this audience. For diffuse reflectance, we're basically interested in a situation where a sample is the illumination and viewing, illumination or viewing geometry is diffuse, so something like D0 or 0D, and actually sort of accurately producing this type of illumination or viewing geometry ends up being the sort of principal experimental challenge. As you can imagine, measuring diffuse reflectance is important anytime you're interested in the optical properties of some material with surface roughness or some sort of bulk and homogeneity. So it finds application in a number of contexts. I'm just listing a subset of them here. One that's important to us at NRC is colorimetry for the paper and textile industries, paint, things like light management technologies and photovoltaics, and also as a spectroscopic tool in various scientific contexts. And of course, for these measurements to be useful, especially in industry, they need to be traceable. So to provide that traceability, national measurement institutes such as NRC in Canada or NIST here in the USA maintain absolute reference instruments for realizing this scale. So basically, if you want to measure diffuse reflectance, what's the 100%? What corresponds to 100% reflectance? Our traceability chain at NRC looks like this. So we have an existing instrument, an absolute reflectometer that realizes a diffuse reflectance scale between 370 and 910 nanometers. We use that to calibrate these pressed PTFE transfer standards. These then get employed in our different instruments to, for instance, calibrate the diffuse reflectance of a client artifact, or in our fluorescence metrology projects to measure things like the total radiance factor of fluorescently whitened paper or something like that. So as I mentioned earlier, the big challenge is really generating that diffuse illumination or viewing condition. So there are broadly two ways to do that. The first is what I would call a gonio-reflectometric technique. This is kind of the most intuitive. Basically, this amounts to measuring the BRDF and then integrating that data set to get, for instance, the 0D reflectance. Alternatively, one can use a number of different integrating sphere-based methods. So here the method relies on an integrating sphere, which is just an optical cavity whose interior surface is highly diffusing and highly reflecting. And so the idea is one optical radiation that enters into the sphere undergoes multiple reflections, with the final effect being that the illumination in the sphere is highly uniform and diffuse. So the method that we have used at NRC for some time and are planning to use on our new instrument is one of these particular integrating sphere techniques, the so-called modified sharp-little method. It's described in this schematic here. So the idea is we have an integrating sphere. The sample is mounted on that sphere. A beam of collimated incident radiation illuminates a well-defined small spot on the opposite sphere wall, and in doing so provides a secondary source of diffuse illumination. We have a detector that's able to view the light reflected normally from the sample or else from a reference position on the wall. And finally, we have a baffle that prevents the sample from directly viewing this illuminated bright spot. And then the baffle is really the key component in a way. So if we consider the shading effect of this baffle in terms of its effect on the irradiance at the sample position versus the irradiance at this reference position at the wall, the sample irradiance is going to be attenuated. And that's basically just because the light, to reach the sample, light has to undergo one additional reflection from the sphere interior. So for an ideal integrating sphere, this is just the average reflectance of the entire sphere interior, which can then be further simplified and written just as the reflectance of the sphere wall times this geometric factor, AW, which is just related to the number and size of these various empty ports. So now if we do our actual measurement, we measure a signal with the detector in two positions and compare that ratio. So that's I sub S over I sub R. And that's just going to be proportional to the ratio of the sample reflectance, rho S, to the wall reflectance, rho W, times this irradiance ratio. And combining that with what I told you about the effect of the baffle, we end up with something like this. And fortuitously, or by design, the wall reflectance cancels out. So we can rearrange this and end up with some expression that gives the D0 sample reflectance in terms of these measurable quantities and this known geometrical term. So this forms the basis then for an absolute diffuse reflectance scale. There's no reference that enters into this. It turns out that this is actually a reasonable way to realize a diffuse reflectance scale. So in the world of national measurement institutes, we establish that through these interlaboratory comparisons. So basically we send, we have a number of labs in different countries that participate. We all measure a similar set of samples. And then we compute what's called the key comparison reference value, which is essentially some average over all those values. And then what we look at, and that's what's shown in these plots, is just how the results returned by a specific laboratory differ from this key comparison reference value. So on the top left is our result. On the right is, on the right-hand side are results from NIST and PTB in Germany. These are both integrating sphere techniques as well. And you can see that between the different integrating sphere techniques, there's quite good agreement. They're all, within the stated uncertainties, they're all equal to 0, which is what you would expect or what you would hope for. They're also fairly consistent with the Gonio reflectometric method, although there is this systematic difference that the Gonio instruments return slightly higher, maybe 0.5% higher reflectances. Okay, so at this point, I'll tell you a bit about our new instrument. So this is a schematic of our existing system. So it's quite a venerable instrument. It was originally constructed in the 1960s. There's nothing, I guess, nothing wrong with that. It still works, but it does have some disadvantages. So in particular, the light source at present is a tungsten lamp that works in combination with a series of narrow bandpass filters. So these are basically the disadvantage of this is that we're stuck with the wavelengths defined by these filters and also the bandwidth defined by these filters. And what's more, the interchange of these filters is also manual. So as you can imagine, this is sort of a pretty laborious process acquiring a spectrum. It's also helpful to keep in mind what the common sources of uncertainty are in this type of measurement. So you would see the usual suspects, things like instrument stability, signal-to-noise ratio, and detector nonlinearity. For spectrally selective samples, we tend to worry about wavelength scale and bandpass effects. And then finally, there's a class of errors or of uncertainties that I'll call sphere non-idealities. So these are basically any factor that's going to make our real integrating sphere that we have in our lab differ from the idealized case. And so this includes things like sample recess, flat sample effects, and sphere homogeneity. The goals for the new instrument are as follows. We are hoping to extend the spectral range from 250 to 1900 nanometers with variable bandpass, full automation, and an improved integrating sphere design that's being designed in order to mitigate some of these sphere non-idealities. This is a schematic of the optical layout. We can divide the system into basically 3 components: a tunable light source, an integrating sphere, and a receiver assembly. The light source is designed to provide tunable quasi-monochromatic light over the target spectral range. Consists of two light sources, a quartz tungsten halogen lamp for use at wavelengths longer than 380 nanometers, and a deuterium arc lamp for use at shorter wavelengths. The spectral selectivity is provided by a Cerny-Turner type grading monochromator. This is a dual grading instrument, so it can accommodate gratings blazed at 500 and 1250 nanometers. This is, again, just so we can cover that full range. We use a series of order sorting filters to suppress second order diffraction effects and stray light, and the input and output slits are continuously variable slits. At the output port, we use a achromatic doublet lens to collect that output radiation and produce a nice collimated beam that we direct into our integrating sphere. Okay, so this is the integrating sphere. Unfortunately, I noticed today when I uploaded my program that, my slides, that there's some artifacts here. And I didn't have time to change them, so I guess the lesson is don't use open source software if you don't have to get things like this. So the sphere is being made, has been constructed out of sintered optical grade PTFE. So this has has good properties for use in an integrating sphere. It's a nearly Lambertian diffuser with very high reflectance between 250 and 2000 nanometers. And for our purpose, it's also quite nice in that it can be machined. So we actually get quite a bit of flexibility in terms of how we can lay out our sphere. The internal diameter of the sphere is about 20 centimeters, and the typical wall thickness is greater than 11 millimeters. This is just because PTFE is a volume reflector, and it needs to be quite thick to become sufficiently opaque. And then the sort of main novel aspect of this sphere is the addition of this PTF, or this what I call a reference port. And this is sort of a design feature that we've introduced in order to try to reduce the effects of sample recess and these flat sample effects. So you can understand that just by thinking through what happens with a more realistic sample geometry. So if we have a situation where we have a planar sample that's slightly recessed from the interior surface of the sphere, that's going to affect the irradiance that this sample receives. So in the case where this remaining spherical section of the sphere is homogeneously illuminated, that irradiance of the sample is just given by this geometric term, this coefficient of radiative transfer, that's defined in terms of these two angles, alpha and beta, and this distance s. And so clearly, just by looking at this cartoon, you can see that the irradiance of the sample will be affected due to an increase in s, the blocking of these high angle of incidence rays, and the lack of self-illumination by the flat sample. So by that, I just mean the fact that a planar reflector can't illuminate itself, in contrast to a spherical section, which will receive illumination from these adjacent areas. And of course, in a realistic setting, you might also worry about reflections from these port edges. So in incorporating this reference port, we hope to match the local geometries of the sample and the reference positions and hopefully divide out these two effects. Another nice thing about having this as a port is we can insert a spherical insert that matches the sphere, and so we should be able to actually measure how big an effect this has. Okay, so the receiver assembly is shown here. It consists of collection optics, 3 detectors, and a rotary stage. The collection optics are spherical and cylindrical mirrors that image the sample or reference wall position onto one of 3 detectors. We use 3 detectors to cover the full range: silicon, a cooled photomultiplier tube, and an extended in-gas sphere detector for the infrared. And these components are all mounted on a rotary stage that rotates about the integrating sphere, which is placed in this location. And this allows the entire assembly to view either the sample or the reference wall position. Okay, so at this point I'll tell you a bit about some of the preliminary data that we've collected to characterize some of these other sources of uncertainty, namely detector nonlinearity, wavelength scale, and spectral bandpass. So we characterized the wavelength scale in the following way. So we looked at atomic emission lines from 3 different light sources, a neon and mercury low-pressure discharge lamps, and the instrument's deuterium light source. We then monitor the output of the monochromator using a silicon photodiode as a function of grading position. And so by analyzing that data, we end up with a data set that relates these true atomic emission line wavelengths to the position of the grating, which is expressed here in encoder steps. We find that this whole data set can be well described by a second-order polynomial, and that produces these modest residual wavelength errors that are on average about 0.01 nanometers. And kind of by experience, we know that for our application, that's sufficiently small. The spectral bandpass is characterized in a similar fashion. So we've looked at lines, 4 different lines from a mercury discharge lamp as a function of slit width, and pulled out the full width at half max by fitting to a triangular wave function. This is the data shown here. And this entire data set is well fit by an expression that's linear in slit width and bilinear in slit width and wavelength. And in fitting to this expression, we end up again with modest residual errors on the order of 0.05 nanometers. So the last thing that we've characterized to date is the detector nonlinearity. So this is something that one generally worries about with photomultiplier tubes. So we've done this using a variable aperture technique. This relies on the principle of light addition and a precision variable aperture that's used to modulate the amount of light reaching the detector. So this is the device shown on the left here. It consists of a pair of blades. These blades are individually positionable via a directly coupled piezo motor, and they're symmetrically arranged about the optical axis. And so in this scheme, we do 3 measurements. We first record our detector reading with the blades completely open. That gives us a reading AB. We then do an additional 2 measurements with either one or the other of the blades completely open and the other closed. That gives us these additional data sets, and so, different readings. And so for an ideal linear detector, you would expect that the sum of these 2 single blade measurements should be equal to the 2 blade open configuration, so we can define a degree of nonlinearity sigma in terms of that ratio. So this is an example data set for our photomultiplier tube for photocurrents between about 0.015 microamps and 1 microamp. You can see there is a systematic trend, especially at larger photocurrents, the nonlinearity becomes more pronounced. However, for photocurrents below about 0.03 microamps, this nonlinearity is modest, about 2 parts in 10,000, which again, compared to sort of the other typical sources of uncertainty in this type of measurement would be expected to make a modest contribution. Okay, so to summarize, a new diffuse reflectometer facility is being developed at NRC. Will feature improved spectral range, variable bandpass, full automation, and a custom integrating sphere. To date, we've characterized some common sources of error I just went over. And the goal is to validate this new scale by participation in this upcoming CCPR K5 key comparison for absolute diffuse reflectance, which is slated to start sometime next year. So that's all I wanted to say. I'll just leave you with the names of some of my colleagues who have contributed to this project, in particular Hugo, the mechanical designer, who was really instrumental in all this stuff related to machining PTFE, and thank you for your attention.